All right, today we're going to be talking about chapter 12, which is shaping the Earth's surface, which is really talking about how landscapes and the hydrologic cycle really affect things like mass wasting. And really, we can look at each one of these landscapes to see what are the different factors going into what cause the landscape to be the way it is shaped. Every landscape is going to look a little bit different and is really a force of all of the tectonic forces taking place, as well as uh, things like the atmosphere, the biosphere, the hydrosphere, which are constantly reworking some of these different landscapes or those different surfaces, creating something we call landscapes. If we take a look at the first image there, that's an image from Rio de Janeiro in Brazil, and we can see that that area is wet in lots of rain in the rainforest, and so it's going to cause these rocks to be nice and well-rounded. We're going to talk about how rivers affect landscapes next chapter in greater detail, but we can see that that area is very well-rounded as a response to uh, the warm, wet environment that they're exposing. If we take a look at image number B, it looks like these are glaciers that were carved from the Alps in France. And we can see that when glaciers come through an environment, they create some very stark, very steep environments, very jagged regions. If we take a look a little bit further downriver, we have image C there, which is a rainforest looking at the Amazon River in Peru, creating this nice broad flat region around a river. Image D are some buttes of sandstone towers above Monument Valley in Arizona. When we have these buttes are in part a function of plate tectonics causing some basin and range topography, and then some weathering smoothing off and eroding these surfaces. Since we get some differential weathering, creating some very unique features there, plateaus, mesas, and buttes. Then we have image E is the Blue Mountains in Australia. And if we can see these very steep regions there, again, caused from water washing away these materials and in this case, some uplift. And then we have some areas that you may be familiar with here in the Midwest, some very flat plains associated with glaciers coming through this environment in, say, northern Missouri would be very similar to that image there, where glaciers have gone and filled in some flat-lying areas. And so each one of these landscapes is very different as a response to all of the tectonic forces, the atmosphere, what's living in it, the biosphere, how the water is affecting this landscape. And so each environment is going to be, again, very, very unique as a function of all of those different regions. So we're going to use the word topography to talk about the area between high and low of an environment. And if we go back to this slide, we can see that the topography of F is very, very small compared to the topography of something like A or B, where you end up with really high highs and really low lows. We can actually use the elevation to measure the difference between high and low, and that's called the relief. Some other things that we can look at is we talked about plate tectonics creating some uplifts, some areas that are causing mountains to form. If you want to know more about that, it's chapter 8 on creating some orogeny, which is talking about these mountain building events. And then we have things called subsidence, where isostatically lower regions creating things like basins. We started looking at slope is the rise divided by the run, or the change in elevation over the distance the area would travel. And so this uplift is causing areas to go up. The subsidence is areas to causing down. And we can actually measure that difference between rise over the run of the river, or the run of that slope, and that is defined as your slope. So we're going to have a steeper slope in the uplifted areas. In areas that are subsiding, those are going to tend to have a lower slope. And so the topography is the shape of the landscape. In the lab class, week one, we looked at topography a little bit more intensely when we started looking at those contour lines. And so these are going to come into play again in this chapter. So there are, when we start looking at plate tectonics, is building up the earth. And then we have erosion, which is removing materials out of an area and then depositing in a further downhill. And so those processes can either be fast or slow, but they are going to be very, very effective at taking areas from high areas and depositing them into the low areas. And so when we start looking at different landscapes, we're going to look at what's driving these different landscapes. And the first thing that we're going to be looking at is something that we've spent a lot of time already looking at, and that's in the form of plate tectonics and volcanoes. The heat from the interior of the earth is causing mountains to start to rise up. And this is going to be causing these driving forces. So things like subduction zones, volcanoes are going to be very, very effective at causing us to have these high mountains. And so whenever we start looking at any of these mountains, again, I'd refer you back to the chapter we've already covered that cause these rocks to get built back up. And now we're going to start looking a little bit more at things that are going to be washing the material down. And there's two different ways that we can do that. The first one is external energy. Now, we know that the sun does not heat up the earth evenly. And so this differential heating of the earth is going to cause us to have wind, air just moving from areas of high pressure to areas of low pressure. And with it, it's going to carry materials that are broken down through weathering. Additionally, heat is from the sun is going to cause water to rise up. And when the water is rising up and falling back down as rain in the hydrologic cycle, what's going to happen is that material is going to wash materials down. So we don't really think of ice being driven by the sun, but ice is driven by the sun in that water evaporates, and if it falls as snow, then it's going to accumulate in higher elevations and carry this material down. One other factor which is going to be really important in driving landscapes is gravitational energy. And this is going to have the tendency for areas of high elevation to get pushed down or as a response, or actually pulled down as a response to gravitational or potential energy. And so when we start looking at mass wasting, this is going to be driven by this potential energy or gravitational energy. So when we start looking at all these different forces that are going to drive a landscape, it's really going to be all of these. Solar being an external energy. So there's a little bit of a repeat in that question. So when we start looking at erosional and depositional landscapes, erosional and depositional landscapes are going to be a function of erosion. And so we'll look at some of the different functions of erosion. We'll also look at the relief. Again, if you have a very high and a low, that's going to create a lot of potential energy where this material can wash down very quickly in the form of mass wasting. In the chapter on sedimentary rocks, we looked at the climate has a real big impact on different types of weathering. Warm, wet environments tend to chemically weather a lot more than any other environment on Earth. And so as a result, you're going to end up with rocks that are going to be more chemically weathered. These rocks aren't as stable and aren't as strong, and so they're going to be more resistant, available to wash down. What is the underlying bedrock? Some rocks are more resistant to weathering. We looked at sandstone, or we looked at igneous rocks, and rocks that contain quartz are very resistant to chemical weathering and resistant to scraping or mechanical weathering. And so as a result, if you had a sample of, say, granite, it's going to stick up a lot easier, and it's not going to wash away nearly as fast as the other surrounding rocks. And so this creates some very unique structures. One that comes to mind is the St. Francis Mountains locally. But if we go further out west, we've got Devil's Tower, where you have these really, really high igneous rocks, which again don't have any cracks for water to wash into, nearly compared to the sandstone around, and the shales and the siltstones, where these sedimentary rocks have lots of pore spaces which weathering can occur. So climate's going to in fact impact the types of weathering, and as a result, it's going to influence the landscape. Then the living organisms. What organisms are around are going to have a big influence on the different types of weathering. One thing that I was not aware when I moved to Missouri is I was talking with a biologist, and they mentioned that earthworms are not native to Missouri. Now this has a big role in why we have the vegetation is very, very different than what it was a couple hundred years ago. The vegetation a couple hundred years ago we had a lot of leaf litter around here, and all those leaves filled in the areas and kept some of the underbrush from growing back up. This explains how you could actually ride a horse through this Ozark area. I do a fair amount of hiking, and I couldn't imagine getting too far off trail with my feet, let alone a horse trying to drive through here. But with the earthworms breaking down the leaf litter, this allows that organic material to be put back into the soil, and allows for undergrowth to grow very much quicker. And so the living organism in my example of earthworms had a real big impact on the landscape of the area around mineral area. And then obviously the amount of time. The longer you have for these different other factors to occur, the more developed a soil profile might be. Probably the classic example on the amount of time is if we take a look at places like Canada, where the glaciers came down from Canada and shoved all of that soil, all of that glacial material down into the breadbasket of the upper Midwest, and it left Canada with very, very limited soil. And so because that soil is now starting at time zero at the glacier's retreat, they do not have nearly the soil development that we have here in northern Missouri. So when we start looking at what are the different factors that are going to influence the landscape, well, climate definitely is. Eroding agent, whether it's wind, which is going to tend to bring up smaller particles, things like gravel would not be able to be carried by wind very easily. Water is very, very effective at moving materials down depending on the speed of that water. So, and glaciers can pick up any size material and carry it down, but when the glacier melts, all of the material is being deposited. I just got done mentioning the time. What is the bedrock or the substrate composition? Well, that's going to be a flow. Whether it's I'm not sure, the topographic map is a map that is just measuring or giving a description of the landscape, and so that's not going to really have an influence on the development of a landform. It just is recording what the landscape, what the landform is. So clearly we know the answer is E. So the next part of this chapter is really getting to this something called the hydrologic cycle. You know it better probably as the water cycle. And this hydrologic cycle is driven by the sun, because the sun is going to cause water to evaporate. And it's a closed system. We're not really adding or subtracting any appreciable amount of water on the earth. And this water is constantly moving back around. It's been moving ever since we've had water on Earth. And this water is being driven around. I was listening to a podcast this week, and they were talking about the hydrologic cycle, and they did a couple of calculations at how much water has been cycling and how long this water has been cycling, and how long the dinosaurs have been around. And about 95% of the water that you're drinking, I know this is kind of a little disgusting to think about, is recycled dinosaur pee. This water is constantly moving around. Now, the vast majority of this water is in oceans, and so if we looked at the vast amount of salt water, by far, that is in the reservoir is in the oceans. About 97 point something percent of the water on Earth is in the oceans. But that water doesn't stay there. The water evaporates and then will fall in as rain or glaciers. Again, as water it's not going to fall exactly in the same spot because we have uneven heating of the Earth, so creating winds. And so that water is going to be falling on different parts of the land and then washing either seeping into the ground to become part of groundwater or running over the landscape. And this is known as runoff or rivers or lakes. Lakes, in most cases, are going to be just wide portions of a river where we're holding these sizable amounts of water. And so when we start looking at which of these is considered a reservoir, well, glaciers are holding, a reservoir is something that is holding this material. And in our case, we're looking at water. So glaciers are definitely holding water. The atmosphere is holding water in it. The rivers are holding water in it. And so if we start looking at which of the following are considered a reservoir on the Earth's surface? Yeah, all of these are going to be. And so if we start looking at the water, we can look at the processes that move this water from one place to the other. This would be the groundwater flow. Evapotranspiration is a term you may not be familiar with. You may be familiar with evaporation, where liquid water turns into a gas. And then if we look at plants, in the process of photosynthesis, we have transpiration, where you're taking liquid water and you're giving off water vapor. And so as a earth scientist, we don't really care how the water gets from liquid state to gaseous state. And so we're going to lump these things together. And many times it's really hard to differentiate between the two. So we'll lump them together and call it evapotranspiration. When we start looking at this hydrologic cycle, this is going to be important, very, very important for shaping the landscape, is this water on Earth. As a result, our landscape looks very, very different and much more smooth compared to other planets that don't have liquid water on them. Without liquid water, we wouldn't have nearly the lack of relief on the Earth's landscape. So I've already mentioned this, but which is the largest reservoir of water in the Earth system? By far, it is the oceans. Glaciers, a second place. If the question was which is the largest reservoir of fresh water, it would be glaciers. The water in the ocean is way too salty for us to drink. We'll talk more about that in our chapter on oceans. But groundwater is about a little less than 1% of all water on Earth. Some of that water is salty. Some of it's too deep for us to obtain very easily. Water in the atmosphere is of these are going to be the smallest portion. Water in rivers and freshwater lakes, those are going to be very important for us for drinking water, as well as for moving of this material through the system. So when we start looking at this water, this is going to have an influence on some of the triggering forces for this thing called mass wasting. Now, mass wasting, you may not have heard before, unless I use the word that the media typically uses to talk about mass wasting, and they'll call these things landslides. Now, landslide has a very, very, very specific term in geology, but collectively, landslides and other forms of mass wasting are in this group of mass wasting called, this title called mass wasting. And these are gravity-driven materials moving downslope under the influence of gravity. So what causes all mass wasting is, in fact, gravity, that potential energy. And again, water can really, really speed up this process in a couple of different ways. So we're going to start from slowest to fastest different types of mass wasting. And the first one occurs right here on campus, as well as everywhere in this region that is not perfectly flat and subject to this freezing and thawing. It is called creep, also referred to as soil creep. So when we start looking at whether it's soil or regolith, broken up bits of rock, what's going to happen is around here, water will seep into the ground, and at night, what's going to happen is, in some days, we're getting pretty close in here, right when I'm recording this in October, we're getting potential to have frost. And if the ground should freeze, what's going to happen is every single grain of material in that water, in the soil will freeze and push the materials away. And if we look at the image here, on the left-hand side, these pieces of soil are getting pushed away from the Earth's surface. And notice it's not straight up, but away from the Earth's surface. And that's a result of water expanding and freezing. When that water thaws, it will move straight back down. Now, this function of freezing and thawing may only move the piece of sediment a fraction of a millimeter, but it's going to happen time and time and time again. Now, the top material is going to be more prone to this freezing and thawing. The deeper you go into the Earth, the Earth itself is going to act as an insulator. And so what's going to happen is eventually you'll get to what's called the frost line. And beneath that frost line, you won't experience any of this creep. And so what's going to happen when the soil creeps is the upper surface is going to move faster than the lower surface. And so if we look at this image on the right here, we can see that upper surface is in fact moving down faster than the lower portion. This would cause trees, which are always trying to grow towards the sun, to actually have a curved growth pattern. And so it's not uncommon at all to have these trees have this curved function. And so if you see a J-shaped hook in some trees around here, also you'd know that you'd be experiencing some form of mass wasting, usually a soil creep. Additionally, if you had a fence post that was put in straight, if the upper portion is moving down faster, what's going to happen is that tree or that fence post is actually going to curve, and so you can actually have fence posts that are no longer going to be straight up as a result of the soil moving. Now, this may take 50 years for that soil creep, for that fence to finally fall, but this is a clear example of this soil creep. This can also happen in areas that don't have freezing and thawing, as raindrops can fall. What can happen is the raindrop causing a splash is going to cause droplet class of material to get kicked up and travel further downhill than uphill. So if you had a heavy rain, more materials are going to get pushed down compared to being tossed back up. So again, multiple times of this rain can cause some of this soil to move down. But again, it's much more effective when we start looking at this freezing and thawing sequence. And around here in Missouri, we have about 90 days of this cycling from above freezing to below freezing. And so we have a sizable amount of soil creep. If we start looking at the permafrost regions, they stay, as the name implies, where the ground is permanently frozen. They don't experience soil creep. They would the ground would be permanently frozen, so we wouldn't have this cycling through of freezing and thawing, freezing, thawing. Also, if you were in an area that was didn't experience a frost, southern Florida would be an example where you very rarely ever get the ground freezing, and so you would not have to worry about this soil creep. The next form of mass wasting is something that occurs only in the permafrost. Now, your book is classifying as a type of creep, but it forms a slightly different way. Solifluction occurs where during the winter months in places like Alaska, the ground is still frozen, but that upper portion can in fact have, if we had an 80-degree day in Alaska, which is not uncommon, what's going to happen is that upper part of the soil is going to be thawing out, and if it thaws out, it's going to start to slide down under the influence of this saturated water. The lower portion of the soil is still frozen in this solifluction, and so as a result, there's no place for this excess amount of water to infiltrate into, and so it's going to just slide down. This is a bit of a problem if you were putting in a pipeline through northern Alaska, and as a result, if you put a pipeline into this region and the soil started soliflucting, it would create a potential for problems. Also putting in railways, we've experienced. I've seen problems where people try to put in a house in this area and they heat up the permafrost. And by heating up the permafrost, you're actually inducing some solifluction and causing your house to slide down, which would be a bit of a problem. The next form of mass wasting is something that we are prone to here in Missouri, is something called slumping. This occurs as a result of gravitational force, where water will infiltrate the soil profile, and the weight of the overlying soil plus the water in that rock will cause the head portion of this slump to have enough weight to actually cause this rotational movement and cause this material to bulge up at the bottom of this slump. And so usually if we have one of these, this area that is prone to slumping, in many times you're going to see these crescent shapes in the headwaters of this area. If we tried finding, oh look, if we find, there it is again. And so if you see one area that has these crescent shaped slumps, look out for other areas in that same region that would experience that slump. So what's going to happen is this entire material is going to rotate up. So the toe of this slump is going to actually have a higher elevation. We start looking at these slumps. The next type of mass wasting is called a mud flow or a mud slide. Now, a mud flow tends to have a little bit more water in it, but a mud slide is also going to be subject to this, formed in the exact same way. When we start looking at a mud flow, this is caused from an excess amount of water, and we've already mentioned that clay doesn't allow water to pass through very easily. And so what can happen is if water hits this clay unit, it has no place to go. It can't seep through further into the ground very easily. And so what's going to happen is it can actually detach from the existing rocks and slide down. And so usually when we have these mud flows, this entire region here will become detached and flow down slope. So this material moves down as one cohesive unit, and it doesn't create a big toe at the bottom. It doesn't have this rotational movement. So that's how we differentiate it from a slump. Mud flows also tend to be a little bit faster. There's a number of videos. If you type in mud flow or debris flow in YouTube. There are a number of different examples of these, and I'd encourage you to take a look at some of these different types of mass wasting events. So there would be a good resource for you to look at. If the material is cobbled boulders and material, they can actually stay suspended in the water. And so if we have a mud flow that contains larger boulders in there, these would be called debris flows. Now in mountainous regions, water in many times, they don't get, in some of these regions, we don't get a lot of rain, but when we do, they all come at once, and water is typically funneled into these river valleys, these steep valleys, so you get all this water in one location, and so it has the potential energy to lift up some of these materials and carry it down as cohesive mass, a fluid. And so what's going to happen is when this settles out, you can actually walk on this debris flow after it has settled, but during the flow, these boulders will act like a very thick liquid. We've already mentioned in our chapter on volcanoes that we're putting out a tremendous amount of ash and water coming out of the volcano. And if we have glaciers melting at the tops of these volcanoes, it can create these mud flows associated with volcanoes called lahars. So what is a mud flow caused from a volcano? Yes, this is a definition of a lahar. The last couple of mass wasting events are called rock slides or rock falls. Now, a slide occurs where we have the rocks sliding down as one cohesive mass. Your book actually has some examples of these. They talk about the Gros Ventre slide in Wyoming, from the right near Yellowstone and Jackson Hole area. And then more recently in Washington State, the Oso rock slide, where these materials have, we've hit we have tilted sedimentary rocks. And if we have these tilted sedimentary rocks, we have, again, a layer of water causing these rocks to detach and slide down as one cohesive unit. If you look at a rock slide, there's a famous one that actually in Japan, if you go into YouTube and type in rock slide Japan, and there was a rock slide that they were filming. They had just set up a camera. There were some signs that this rock slide had a potential for going out, and so they had just set up a camera in this area. They heard some popping, and they shut down this highway. And as soon as they put the camera up, they were able to see this rock slide where this whole material slid down the hillside. And then when they pan out to the aerial footage of this, they can actually see where these rock slides had occurred in the past. But this rock slid down as one cohesive unit. A rock fall is where the rock will literally fall vertically down. And so we can see in this pile here, this pile at the bottom of this image here, this pile of scree or sedimentary rocks rocks of any sort, which are piling up at the bottom of this hill. It's sometimes called the talus slope, where the rock has literally broken off, fallen under the influence of gravity, and accumulated at the bottom of this material. One of my classic examples of this is found on the New Hampshire State Quarter, where there was a photograph of the Old Man in the Mountain. And it was newly minted at that time, back around 2000. And the Old Man in the Mountain was named after this granite structure on the Atlantic Ocean, showing this profile, which kind of looked like an old man, and it was literally called the Old Man in the Mountain. It was a symbol of strength and stability. Unfortunately, gravity and wave action undercut some of these rocks, and so what happened is this Old Man in the Mountain, within a year of being minted and having going out as a symbol of their state quarter, the Old Man had underwent a rock fall where the man got a facelift. Well, just the opposite, where these rocks literally broke off and fell into the ocean. And so again, if you'd like to see that, type in Old Man in the Mountain, and you can see the before and after as a result of this rock fall. If you were looking at a piece of property around here, we have found some of these rock falls. We have put in some highways, and as a result, we have cut into the existing rocks, so we're not driving like this. We're driving on a straight line, which means that some of these rocks are going to be very steep, prone to these rock falls. Now, engineers try their best to make sure that when they're blasting away and cutting these materials back, they do not want to go above what's called the angle of repose. And the angle of repose is defined as the steepest angle which material can be built up to without having a collapse. Now, if you had something like sand, the angle of repose would be 30 degrees. Now, if you had that same sand with some water in there, you can now build a sand castle and actually get it to become vertical. But as the sand starts to dry out, that angle of repose would go back down to 30 degrees. And so if you had irregularly shaped gravel, you can actually build it up to about 45 degrees. And if you had silt, you can actually get it above 90 degrees. There are some areas just east of us, right along near the town of Chester, Illinois, where you can actually see some examples of silt deposits that are really close to 90 degrees and stable at that point. You can go a little bit further up on the Illinois River to Peoria, where you have 100 feet of silt, which are, again, really close to that 90-degree angle. But depending on the material, different materials are going to have a different angle of repose. And if you're at the angle of repose or above the angle of repose, you're prone to these mass wasting events. Another form of mass wasting is called an avalanche. A snow avalanche is when we have this rapid movement of material downslope, and it's going to behave as a turbulent cloud of material. We can also have an avalanche not made of snow but of debris. Again, during these avalanches, this material is mixed up, and in avalanches, both debris avalanches and snow avalanches, in some cases it can actually trap a pocket of air at the bottom of this avalanche, and as a result, it's going to, this pocket of air is going to make this rock act like an air hockey puck and go for long periods of time and allow these materials to reach speeds of hundreds of kilometers per hour. Mass wasting can also occur beneath sea level. And so as a result, what can happen is we can end up with a submarine slump, a submarine debris flow, and if it's a slump, it's going to have this detachment and have this toe that's building up of material. But if we undergo a debris flow, it looks a little bit different in that heavy stuff is going to fall out faster than some of the smaller materials, and so we'll end up with a turbidity current and a graded bed. I know that we already talked about that in our chapter on sedimentary rocks. So here's an image of some of these underwater debris flows, and so we can actually see this example right here would be a slump, creating that toe where we end up with this rotational movement. And if we were to look underwater, this is a simulation of one of those turbidity currents where we end up with these pile of material having this heavier stuff deposited faster than the upper portion. And so this, what do we call these materials where we end up with this heavier stuff being deposited faster than the upper portion? And these are called turbidity currents. So when we start looking at different types of mass wasting, these different types of mass wasting, we can really see how the landscape is being altered in response to these different types of mass wasting. So what causes a mass wasting anyway? Well, whenever we're going to experience a slope failure or a mass wasting event, we're going to have a point where the resisting force, or the force of friction pushing up, is less than the driving force, the force that is causing this material to mass waste. And there are some things that can really can be called triggering events. And if we start looking at these triggering events, these can lead to failure. The first thing that can happen that you can look at as an example would be ground shaking. Obviously, this ground shaking can displace some of this material and cause this material to trigger a mass wasting event. And so many times after an earthquake or during an earthquake, this triggering event can cause some of the mass wasting. You may have heard about in 1811, the earthquake was so strong that it caused the Mississippi River to run backwards. Well, what happened was it definitely did cause some shaking, but it caused a mass wasting event that caused some of the river to, the river valley to be filled in, and the river had to change its course. And so it did, in fact, cause the river to move backwards as a response to this sediment. As a result, we have places like Reelfoot Lake, where the river, in fact, changed its course and it abandoned an oxbow. More on that in an upcoming chapter. Some of the other things that can cause a slope failure is the change in the amount of support. So if we were to, say, reduce the resisting forces, you could do that by maybe extracting some of this rock. Or the other thing that you could do is you could increase the driving forces. And one of the ways that you can really do this is by adding water. So we'll talk about some of these different forces here. But anytime that you have more driving forces than resisting forces, you're going to have a mass wasting event. So what are some areas that are more prone to mass wasting? First of all is having a failure surface. We know that we have joints or cracks in rocks, and these are areas that are going to be subject to mass wasting. These cracks are going to allow water to pass in. Well, this water has to go somewhere. So if we had a weaker surface, maybe due to unloading of the surrounding material. And so what's going to happen is we're going to end up with an area that is going to be much more prone to mass wasting. If we take a look at a place like Elephant Rock, Elephant Rock has all of those rocks of boulders of elephants all on one exfoliated surface. If we use geophysical techniques, we can actually see that there's a second layer of exfoliation joints on that granite. And so our Elephant Rock, again, has a series of joints that are going to be more or less horizontal. But if these rocks were a little bit closer to, had some angle associated with them, not horizontal, it would provide a conduit for water to go, and it would create a weaker surface here. If we have a layer of shale, remember that shale does not allow water to pass through, and if the shale doesn't allow water to pass through, it can actually hold water, and this creates some problems because water is going to fill in those pore spaces, increase the driving forces. Water is also going to act as a lubricant, decrease some of the resisting forces. So water has a multi-pronged approach for triggering some of these mass wasting events. The energy is still potential energy or gravitational energy, but water just enhances the ability for that potential energy to cause a failure. Metamorphic rocks, which have a foliation associated with them, that foliation direction can cause rocks to fail. So some classic examples that I've already mentioned that your book talks about are the Gros Ventre slide. In 1925, there was a rainfall event which again allowed water to seep into the ground and move all along that surface. That surface had extra water, increased driving force. The water acted as a lubricant here, and as a result, it caused this material to wash down into the Gros Ventre River. And so all of this material now blocked the river. And so not only did it cause a problem for anyone who is living down in this portion of the underneath the slide, but anyone further downhill, because if this lake, which was being fed by water constantly moving downhill, this water had no place to go. And so the fear was, if this water wasn't allowed a safe way to be drained, it would overtop this landslide material and wash down and cause a torrent of water to come down. And so the Army Corps of Engineers worked really hard to find a safe way for this water to go through, and they had to work against the clock because their time was as fast as this water was filling up above. And so this could have triggered a secondary problem. Another example of some mass wasting event can be occurring through wave action, where this wave action is breaking away the rocks at depth, and as a result, we have this joint increasing the driving forces and no resisting forces underneath because of this overhang causing this rock fall. In the spring, we have heavier rainfall, and so particularly in mountainous regions, spring can be very, very deadly in terms of mass wasting events. These mass waste, in this case, in 2014, in Oso, Washington, what happened was heavy rainfall and the ground thawing out as a result of spring warming. Water seeped into the ground, hit a layer of material that was not allowing water to pass through anymore. It's built up. The water decreased the resisting forces and added the driving forces, added some weight, and so as a result, this large mass wasting event took place. And unfortunately, the town of Oso had some residents in there, and they were buried by this huge pile of sediment. So when we start looking at some of these different features that are going to maybe warn of a slump or any of these mass wasting events, really, we can start to see things like tilted utility poles, sinking foundations as this material is moving downhill, as well as some broken fences. So if we started looking at what are some different forms of that would potentially cause you to be alerted of a mass wasting event, unfortunately, if you saw any of those, you may want to be prepared, maybe wanting to be prepared for the event of a mass wasting event. So unfortunately, when we start looking at these mass wasting events, these aren't covered by standard homeowners insurance. And so there's a town of La Jolla, California, just a suburb of San Diego, which unfortunately, about 100 homeowners were impacted by a mass wasting event. And this mass wasting event, the homeowners realized that there was some water that was leaking from a pipe. And so the question was, did the pipe cause the mass wasting event, or did a mass wasting event caused the pipe to leak. If the mass wasting event caused the pipe to leak, then the mass wasting event was the problem, and there was no one to blame. But if it was the pipe that caused the mass wasting event, then the city would have been on the hook for repairing, paying for those homes. And so it actually went to court, and a couple of years later, it was found that the burden of proof was on the homeowners to prove that the pipe caused the mass wasting event. And unfortunately, they were not able to do that. Unfortunately for the homeowners, they weren't able to do that. And so as a result, they had to pay for all of the damages that were caused themselves. So when we start looking at the strength, the changes in the slope strength, obviously weathering is going to have a big impact on this, both mechanical and chemical weathering. Mechanical or physical weathering can break these rocks apart, and that's going to decrease the resisting forces. The amount of vegetation can play a role. Many times around here, you will see when a roads department blasts out a new road, what will commonly happen is they will actually spray seed cover and maybe even put in a geotextile, which is basically a fabric which is going to simulate the root structure until these plants can take hold and hold the soil in place. And so the vegetation in many cases is going to strengthen the slope and increase the resisting forces. Water content, as I've already mentioned, is going to add weight. All those pore spaces which had air and are now filled with water are going to be increasing the resisting forces, and they're going to reduce the so water is going to increase the driving force and reduce the resisting force, in that it can actually decrease soil cohesion. It can make the water get in between those individual clay particles and make it real slick. If you've ever tried to stop in a mud or try to run in a muddy environment, you can see you've experienced the decrease in soil cohesion associated with clay and water or mud. And so water pressure itself, again, is going to, the weight of the overlying water pressure can push those particles apart. And so one of the things that you can end up doing if you saw that your area was prone to mass wasting is a couple of different things. One of the things that you could end up doing is putting in some, in this environment, you may notice that this mass wasting event, let's take a look at this slump here. We can see that some pools are starting to occur. This slump crescent scars are starting to appear, and say, oh no, this area is going to be prone to mass wasting. And so one of the things that you could end up doing is putting in some rock bolts, which are basically big poles which would hold this material in place. Other things that you could do is drain this soil. If you got rid of the water, maybe put in some gravel riprap that would actually allow this water to pass through much faster. So those are some things that you could end up doing to prevent some mass wasting. And those things would be costly, but they could in fact save structures. And so that would be a possibility. The other thing that you can do is know before you buy. Look at a potential landscape map, landscape potential map. This is one of the western United States. These are areas that have some fairly steep mass wasting. And you'll notice that places like western, right along the coast, we've got erosion associated with the wave action, but even further inland, you have those mountain regions, those areas with a very steep slope. And so if these are a steep slope, they're going to be more prone to mass wasting. So again, some of the other things that you could end up doing is revegetating a plant, an area, and putting in vegetation this could stabilize future mass wasting events. The other thing that you could do is terrace, remove, redistributing the mass. And so by removing this material up here and putting it down here, one of the things that you end up doing there is decreasing the driving forces and increasing the resisting forces. Reducing the subsurface water, putting in drains, and if you were able to somehow get rid of that water, in this case, they're lowering the water table. They're pumping out that water out of this region, and as a result, increasing the or decreasing the driving forces in this case. Maybe preventing some undercutting, putting in some riprap or broken up bits of rock, which would stop some of this wave action from undercutting this material, or filling in some channels. In this case, they diverted a river to not start cutting away at this bluff, and the rerouted river here is not going to cause some of this undercutting in this area. Some other things that you can do retroactively is to put in a retention wall. This retention wall would be basically a pile of concrete, but it would trap any of this debris from potentially going onto these roads. I mentioned those rock bolts. Those rock bolts would be acting like those vegetation anchors. Putting in an avalanche shield. I've also seen in places like down 44 on our way to southwest Missouri, what they'll end up doing is putting in a steel mesh net that would actually stop any of this debris from falling off. So what are some following, which of the following are used to help prevent mass wasting? Well, weathering definitely is. Excuse me. Revegetation definitely is. Weathering, well, we can't really stop weathering. We can prevent undercutting, as we said. We can stop some wave action from undercutting. So definitely prevent mass wasting and revegetation. Weathering, well, that would actually cause an decrease in the resisting forces. And adding of water, we already said, is a bad idea because it's going to increase the driving forces and reduce the resisting forces. So clearly it's A and E. So when we start looking around on campus, what are some areas that would be potential for mass wasting? I would say right along 67, where you end up with a steep slope where mass wasting could very easily, frost wedging could actually pop off those pieces of rock and have them fall into the ocean, onto 67. It's not uncommon along the highway like 67. If you go a little bit further north, we've had multiple occasions where we've had different types of mass wasting. On the eastern side, right by Big River, one of the big pieces of rock have fallen off to cause this mass wasting event. On the western side, on the southbound side, just a little bit further north near St. Francis State Park, we have had a slump occur, and you can see the scar of that slump on the road. So we've had some multiple examples of these mass wasting events. So I encourage you to look around. In addition to just looking on campus, we can look over by your house and see if there's any place that would be prone to mass wasting.